So we were talking about Henry's law in the last video, and remember that was the partial pressure of a liquid will equilibrate to that of a gas that surrounds it. And we saw the application of Henry's law when we looked at the partial pressure differences within the body. So what we're going to do is we're going to go through a couple different scenarios here and look at what the partial pressures are. Remember, partial pressure is important because it's the partial pressure difference that drives gases. Gases diffuse from a high partial pressure to a low partial pressure. To get that partial pressure, the easiest way to do it was to use Dalton's law, especially in an atmospheric condition, and take the percentage of that gas and multiply it by the total pressure, and that would give you the partial pressure for that gas. So let's look at the condition for oxygen. So see the PO2 up here. That means the partial pressure of oxygen. So again, looking at the PO2 up here, the partial pressure of oxygen, right? In room air is 159. So we see that right here, room air, the PO2 is 159 millimeters of mercury. Remember, the pressure units that we invariably use for just about anything physiologically are millimeters of mercury. Sometimes they use what they call centimeters of water pressure in some respiratory variables, but we're not going to use them in this class. It's always going to be millimeters of mercury. Now, how do we get 159? Well, this is sea level. So remember, sea level, we say, oh, the pressure is 760, total pressure. And then the percentage of oxygen in the room air is 20.93%. So to go into decimal, it's 0.2093, and that's going to give me 159 millimeters of mercury. So we take the total pressure times the percentage of the gas, in this case it's oxygen, and that gives us 159. Again, we know it's 760 because we're talking about sea level. The resting is important because that tells us what's happening in terms of metabolism and what's happening at the tissue level. So as we breathe in this air, right, and exchange it with our lungs, that's called ventilation, right? As the oxygen goes into the alveoli, notice we go from 159 to 105. So 105, what happens is the oxygen gets diluted as it moves into the alveolar spaces. And that's because oxygen, whether you're breathing in, breathing out, holding your breath, is always exchanging. It's always leaving the alveoli and moving down its partial pressure gradient into the capillaries in the lungs, or the pulmonary capillaries. It's probably the better way to say it. So it gets diluted, okay? In the alveoli, we call it P capital A. That capital A stands for alveoli, right? O2. So the partial pressure of oxygen in the alveoli at sea levels for humans is about 105. Once we know that it's 105 in the alveoli, as the blood moves through, the partial pressure of a gas, the air in the alveoli, right, will cause the partial pressure of the liquid, that's the blood, to equilibrate. So once blood comes out of the pulmonary capillaries, because of Henry's law, we get the partial pressure of oxygen at 105. So again, if the alveolar oxygen was 130, it would come out at 130. If it was 70, it would come out at 70. So it just really depends on what the partial pressure of the alveoli are in terms of the oxygen content. Now, what happens is as we move through the systemic circulation, there's no exchange that happens, but notice we go from 105, and I'll draw the arrow to the entrance of the capillary system for the systemic side, and notice it drops down to 100. And the reason why it drops down to 100 is what we call this venous admixture. Okay, so notice we have an arrow starting on the venous side and going all the way over to the arterial side. And so the venous admixture is a bit of blood that has a low amount of oxygen in it, relatively speaking, and it bypasses the lungs. Sometimes it's called a shunt. And it bypasses the lungs and ends up dumping into the arterial tree. So what it does is, since it's lower oxygen, it dilutes the partial pressure of oxygen down a little bit, down to about 100. So at the entrance of a systemic capillary, the partial pressure of oxygen is about 100. Now, if we look at our tissues are using oxygen, right? And so it's going to be lower. So if we come in at 100, the arrow goes down. That's because we're driving gas, right, into the tissues down the partial pressure gradient. We're not using all of the oxygen, though. And there's some just hanging out. So the partial pressure drops down to about 40. That's a number you should know, you should memorize. The normal partial pressure in tissues is about 40. Now, this has the same application as we saw with the alveoli. We can apply Henry's law again. If we know the tissues are 40, the exit's going to be 40, right? And these aren't going to change as much as the alveolar space. But if the tissues go to 50, then the exit's 50. If they go to 38, the exit's 38. All that matters is if we know what the tissue is, by Henry's law, we can figure out, right? So by Henry's law, we can figure out what the exit's going to be. Now, as blood moves through the venous tree, right, it doesn't do any exchange. Even though we lose some venous admixture, it's at the same concentration of everything else, so it doesn't affect anything. And we're back to the entrance of the pulmonary capillaries. Now, the entrance of the pulmonary capillaries, we didn't really mention it before, is 40. And the reason why it's 40 is because the tissues were 40, right? And so since they entered the systemic capillaries at 100, the tissue was 40, so gas diffused in until it equilibrated because of Henry's law at 40. It exited at 40 and then traveled through the venous side until it entered the pulmonary capillary at 40. Again, going back to the alveoli, since the alveoli are 105 and the partial pressure of oxygen in the pulmonary capillary, the venous side, is 40, gas is going to diffuse in, right? So it's going to move across the respiratory membrane into the capillary until it reaches what number? 105. Because of why? Henry's law. So you can see that that's the way it looks for sea level at rest. Now we'll look at what happens when we look at sea level and rest still, but this time we're going to look at PCO2. So the PCO2, the partial pressure of carbon dioxide, right? So look up again here in the upper left. Right, we're going to look at the partial pressure of carbon dioxide at various points of the ambient air in the body. So again, we're going to stay with that same condition we had before. Sea level, which tells us what the total pressure is, and rest, which tells us the metabolic state of the person we're considering when we look at these problems. So remember, sea level is 760 millimeters of mercury. We would multiply that by 0.00004. It's actually 3.5, but we'll round up. And that's the percentage of carbon dioxide in the room air. Notice it's much, much lower than what the oxygen is, yet depending on what source you read, carbon dioxide is the third or fourth most abundant gas in the atmosphere. It's kind of a misnomer a little bit, but remember we said that the nitrogen was 0.79, so we'll just go ahead and make that. And the oxygen we said before was 0.2093, and that gives me 0.9993. So that means we have 0.0007, that's it, left for all the other gases that weren't included in those first two categories. So CO2, you should know this number, right? It's 0.04%. So if we're doing the fractional equivalent, we divide that by 100. So we get 760 times 0.0004, and that gives me 0.3 millimeters of mercury. What happens when we inhale room air, though, is the opposite of what happens with oxygen. So remember, the oxygen diluted, it went from 159, in the room air to 105 in the alveoli. But this time, we're actually going to concentrate the CO2. So we go from 0.3, right, into the alveoli. That goes up to 40. Right, so it goes up to 40. So 40 millimeters of mercury would be the P-A CO2, the partial pressure of CO2 in the alveoli. That's what the capital A stands for again. So really, it's not dilution. It's probably more concentration as to why the partial pressure of CO2 goes up. All right, so once we know the alveolar CO2, what's it going to come out at? Well, the exit of the pulmonary capillary, because of Henry's law, right, is going to be 40. So this is 40, right? And because of Henry's law, this is 40 as well. As it travels through the arterial tree, there is some venous admixture. It does have a slightly higher CO2 content. And this, you could argue, goes to 41 maybe. But, let's stay with kind of these bigger numbers. So we're going to say it's not big enough to affect it. So we're going to say the entrance of the systemic capillary, right? The partial pressure of carbon dioxide is going to be 40 still. Now, the tissues are using that oxygen and through metabolism producing CO2. So it makes sense that the CO2 is going to be higher than the blood. In the case of the tissues, in this case, it's 45. That's a good average number. Some books use 46, but again, we'll stay with 45. And because the partial pressure of CO2 in the tissues is 45, and in the capillary it's 40, then the CO2 is going to move from the tissues into the blood. And it's going to keep on doing that until it reaches 45, because the partial pressure of a liquid, the blood, will equilibrate to that of the gas that surrounds it. That's considered to be the tissues. So it'll exit at 45 because of Henry's law. As it travels through the venous tree and then the entrance back to the pulmonary capillary, it's still going to be 45. So when it's 45 in the blood and 40 in the alveoli, we're going to go ahead and diffuse the CO2 from the pulmonary capillaries into the alveoli, and then through the active ventilation, they're going to go out the alveoli and into the room air, or sometimes known as the ambient air. So that's the partial pressure differences that drive gases for sea level and rest for CO2. But sea level is not the only condition we really should worry about, nor is rest. So we're going to look at two other conditions and kind of see what happens. So the first one will, went one too far, will be sea level and exercise. So instead of looking at sea level and rest, we're going to look at sea level and exercise. So look at exercise then. Sea level tells us the total pressure, and exercise tells us what the level of metabolism is. So we'll kind of look at the differences and how that's caused. And like we did before, we'll look at the partial pressure of oxygen first, and then we'll look at the partial pressure of CO2. So since we're at sea level, right, the total pressure is going to be 760 again. Again, it doesn't matter what the percentage of oxygen is, as long as we're in the atmosphere. It's 20.93%. So the ambient air of 159 is not any different for the PO2, the partial pressure of oxygen in the ambient air. It's still 159. Now, as it moves into the alveoli, it gets diluted like we saw before, but there's a slight difference. If you'll notice, the number is still 105. And the reason why it's 105 still is this word right here, hyperpnea. Okay, so hyper is increased, pnea refers to breathing. And what hyperpnea really means, hyperpnea, what hyperpnea really means is an increase in breathing to meet metabolic demands. So what happens is we increase our breathing during exercise that helps to keep the alveolar partial pressure, the P capital AO2, at 105. And so that's how this works in terms of ventilation and maintaining our alveolar oxygen. There's been a whole bunch of studies done that has verified this in multiple ways. So it doesn't matter whether you're exercising or at rest. If you're at sea level, the alveolar O2 is always going to be 105 in normal person. And for the person who's exercising, it's because of that hyperpnea we talked about, increasing the respiration to meet metabolic demands. So if we know the alveolar space is 105, then we know the exit is 105 because of Henry's law. We still have this venous admixture, which still drops this 105 down to 100 eventually. And so when we enter the systemic capillaries, we're at about 100. Now the tissues are a little different. Okay, and again, this side, if we look at just the arterial side that I have right here, all of this right here, all of this is exactly the same as it was for rest. Where it changes is here in the tissues. Now, the tissue in the resting situation was at 40. We don't see that 40 anymore here because we don't have as much oxygen hanging around, because the tissues are more metabolic because we're exercising. There's less oxygen hanging around, so the PO2 in the tissue goes down because we're using it up. So the partial pressure of oxygen in the tissues at exercise, for this example, I used 10, but it really depends on the level of exercise. If you're slowly walking up the stairs from your car to a classroom, it might go from 40 to 38. But if you're exercising fairly vigorously, it can go all the way down to 10 or even lower. So here's this person that's exercising fairly vigorously. Their partial pressure in their tissue goes down to 10. Once we know in the tissue it's 10, it comes out at 10 because of Henry's law. So if I said, oh, it was 18, it would be 18 on the exit, or 36, it would be 36 on the exit, and so on. Like we saw before, as we move through the venous tree, it stays the same. And once it enters the pulmonary capillaries, right, now it's 10. And the alveoli, because of the hyperpnea, right, drives oxygen in faster, right, until it equilibrates to 105 because of Henry's law. So that was for oxygen, and we should see a similar one for CO2. But before we get to CO2, let's talk a little bit about the pneas, right? And many of you have seen this before, I'm sure, and most of you probably know. We said, oh, somebody has sleep apnea, right? Most of you probably realize that when they're sleeping, their breathing stops, right? And so pnea, right, that root word is going to mean breathing, and the apnea, the A, means without, so that's what apnea comes from. But here's some different things to think about. We kind of mentioned them, but we haven't actually defined them formally like we're going to do now. So the first one I want you to know is called eupnea. The EU root means true or normal. So eupnea is a fancy scientific way to say normal breathing. If I want to increase my breathing, it makes sense if we call it hyperpnea, hyperpnea, increased breathing. But in this case, it sort of has this underlying understood condition that is breathing to meet metabolic demands, that we're increasing our breathing rate because we've had an increase in metabolism, right? Don't confuse hyperpnea with hyperventilation. Hyperventilation is different. It's excessive ventilation. It's excessive breathing. It's more breathing than you need for the metabolic condition. And in hyperventilation, we're going to get rid of excess CO2, as we kind of saw in lab a couple ways in the past semester. So hyperventilation is excessive breathing, and sometimes it's known as tachypnea. Okay, so tachypnea. We saw tachy before for tachycardia, right? So instead of the heart cardia, we're at pnea, which is breathing. So most of you probably figure it out that tachypnea is increased breathing. And then we also sometimes people use polypnea. Okay, so poly, many, pnea breathing. So that's also an increase in breathing. And all three of these are actually hyperventilation, just another way to describe hyperventilation. Now, one of the concerns sometimes by individuals is something called desaturation. And what desaturation means is we have a decrease in the oxygen carried by the arteries because basically we're not getting the ability to put oxygen into our blood vessels and get that into our blood. Humans, it doesn't seem to happen. Even in the best of athletes, we don't seem to get desaturation. However, some high performance animals, thoroughbred racehorses, greyhounds, cheetahs have been known to do this as well, do have some degree of desaturation, but in humans, we don't. And desaturation would be bad because you don't have as much oxygen as you theoretically would want within your carried in your blood. So that's kind of a couple quick odds and ends. Let's look at the sea level and exercise for CO2. The thing to note about CO2, again, we're at sea level, so that gives it our atmospheric pressure. We're going to assume is 760, 1 atmospheric pressure at sea level. We're going to say we're exercise, which determines the metabolism. And just like we had for the oxygen, right, the room air is the same because we're at sea level, so we have the same total pressure. The percentage of carbon dioxide is the same, 0.0004. We would multiply it by. The alveolar CO2 is the same as we saw with rest. And again, that's because of the hyperpnea that keeps CO2 levels normally. When it exits, it's at 40, right? 40 because of Henry's law. As it travels to the arterial side and through the entrance, right? We have a slightly different situation now. Because the tissues, we're using more oxygen. So because the tissues have a higher oxygen utilization, it should be no surprise then they're going to produce more carbon dioxide. So the PCO2, the partial pressure of carbon dioxide in the tissue, goes up. We can see 45 was normal. We looked at last time. It might go up to 50 here. Since we have 50 in the tissue and 40 in the capillary, right, gas diffuses in. And it diffuses in until it reaches 50, the tissues, right, because of Henry's law. It travels through the venous side to the entrance of the pulmonary capillaries, right, as the same number, 50. And then when it enters the alveoli, pulmonary circulation, the alveoli have a partial pressure of 40. The pulmonary capillaries have a partial pressure of approximately 50. Since the diffusion gradient is from the blood to the lungs, we're going to diffuse that gas into the lungs, and the person's then go ahead and breathe it out. So again, just like we saw for the condition last time for oxygen, the inlet side stays the same, right? So all this is pretty much the same number. And it's when we get to the systemic capillary where things typically change for sea level and exercise. Now, there's one more we can do as well. Would be what happens at altitude. So at altitude, right, there's a couple things to consider. First of all, is the partial pressure of oxygen enough to sustain life? Remember we said that the minimum is 50 millimeters of mercury, and that's about it's actually a little less of the top of Mount Everest under most conditions, most days. All right, so we'd have to fill these numbers in just like we did before. All right, so we'll worry about the next one. So at room air, right, when we're at altitude, what happens to the partial pressure? So looking at this condition, there's a couple things we can say. So first off, at altitude, we didn't say what altitude it was. And you have to define what the altitude is, or at least what the total pressure is, so you can do your calculations. So we went up to about 18,000 feet. And at 18,000 feet, 18,000, At about 18,000 feet, the total pressure is about 380 millimeters of mercury, so 380. Why that is significant is 380 is half of 760, which is the total pressure at sea level. So if we say, okay, we're going to go to 18,000 feet and make this 380, we still multiply it, right, by the by the fractional equivalent, so 0.2093. And if you do that, you'll come out to the magic number of about 79 millimeters of mercury. We can also say, since the total pressure is half of what it was at sea level when we're at 18,000 feet, the percentage of oxygen doesn't change. So we can say, okay, the pressure's half as much, the partial pressure is going to be half as much. So as we move through the system, we will see the numbers that we were looking at before. Hold on. So we'll see for altitude at rest, there's no equation to figure out what happens to the alveolar oxygen or CO2. We know it's going to be less in the case of oxygen because of that dilution factor. But most of these numbers come from studies where literally they stuck a tube down someone's nose and measured what the actual partial pressure of oxygen was in those situations. So the oxygen goes down to 60 there. So since we know the alveolar oxygen is 60, what's going to come out at? Well, it should be the same because of whose law? Henry's law. So we see 60 there. And then in the arterial tree, it's 60. Yeah, there's a venous admixture, but it's not a big enough difference to change much to worry about. So yeah, it might go down to 58 or something, but for the most part, we'll leave it at 60. So it enters the tissue at 60. Now, when you're at altitude and resting, it doesn't matter what, it doesn't change the amount of oxygen. Yeah, the worker breathing's a little more, so it increases your metabolism slightly. We're not going to even worry about that small change. We're just going to say, okay, if you're resting at altitude, it's not any more different to sit in a chair at altitude, do nothing, than it is to sit at home and do nothing, right? So at sea level. So the tissue partial pressure is similar. And then because of Henry's law, it exits. So the tissue is going to be 40. It exits at 40, right? And then goes to the venous tree at 40. When it gets the lungs, right, it enters at 40 and then diffuses in until it equilibrates at 60. So this is why it's more difficult to breathe at altitude. It's not the percentage of oxygen that matters. It's the partial pressure of oxygen. And notice this partial pressure difference, 60, right, and 40 here is not nearly as big as 100 compared to 40. So because of those larger pressure differences, we're able to drive more oxygen into the blood at sea level. So there's all the numbers, right? What's good about the partial pressure of CO2 is it doesn't change at all. The room air was 0.3 at sea level, and now at altitude, it's half of that, so 0.15. So it's a half of nothing, basically. It's still nothing. The alveolar oxygen is still 40, right? The exit of the pulmonary capillary is 40, and it stays through that. The tissue, because we're using oxygen in a small amount at rest, right? So the tissue is 45, it exits at 45, and then it goes to the venous tree at 45, enters the capillary, and then diffuses into the alveoli, where then we ventilate it out. A couple things, to think about, and here's like a little way to remember it at least, is one of the things we've been discussing a lot and brought up in many, many different instances in the last couple sections has been that it's the difference in partial pressure or the difference in concentration or the difference in percentage, whatever it is, right, drives the movement of fluids, whether it's blood or urine or gases. It's that pressure difference that we have to worry about. And so sometimes students go, oh, I remember that CO2 has something to do with 45 and 40, but I don't remember which one. Well, if you think about it, where does CO2 have to go? It has to go outside the body, right? So since it has to go outside the body, it has to be higher in the systemic capillaries and lower in the alveoli. Otherwise, gas wouldn't move out of the body that way as far as CO2 is. If you look at the opposite way for oxygen, right, most students remember, oh, it's 100 and then 40. And some students sometimes get that idea backwards, but it's okay, if I know that oxygen is going to be highest outside my body and I need a gradient to move it into my lungs and then a gradient to move it into my blood and then a gradient to move it into my tissues, then if I remember the highest number is about 105 and the lowest number is about 40 within the body, then you can kind of stepwise the different things and it makes it a lot easier. So that's the partial pressure differences that drive gases under different conditions. Now, if you've been paying attention to the semester, looking at things, a good student might think, wow, he talked about sea level and rest and sea level and exercise and then an altitude at rest. But let's look at the next slide. It has nothing to do with what we were just talking about. So I am not going to ask you, so don't worry about altitude and exercise. Theoretically, with the information that I was giving you previously, you should be able to figure it out, but I'm not going to ask you in an exam situation in order to do that. So this seems like a good place to stop this one and pick up the next one for looking at maybe the rest of the respiratory system. Who knows?